All right, guys, next example problem here that I'm going to work out for you. Here it says the reaction below takes place in water and in a bomb calorimeter. If 50 grams of ammonium nitrate decompose in 100 milliliters of water, how many kilojoules per mole of energy is absorbed in the chemical reaction if the temperature of the water changes from 30 degrees Celsius to 15 degrees Celsius? So here you see the reaction, and then you also have some details that I added over to the left-hand side. All right, so let's get started here. So this says it happens in a bomb calorimeter in water, okay? So there's going to be that's important information. There's going to be a transfer of energy. If you guys remember how we did the calorimeters, we took the temperature of the water. It's really hard to take the temperature of a chemical reaction, but it's a lot easier to take the temperature of the energy of that reaction as it transfers from one place to the next. So here it says the water temperature changed because, the water temperature changed because of the reaction. Okay, that's why it happened, because of the reaction. Okay, so that's important. So I also want to say, ask this question of you of where did the energy go if the water temperature, if the water temperature decreases or decreased? So that's an important question to consider too. Where did the energy go? As you start a question like this, it's important to think about where energy's going. Where is it starting? Where is it ending up? What do those numbers look like? Because there's positives and negatives in here. We want to make sure to have that straight. Okay? So it's an important thing to think about. Maybe just for fun. Can you draw a model? You never know when I'm going to ask you to do that on a test, right? So can you draw a model? I might ask you to. I might not, but I love to do that. Okay, so what are we going to do? Let's solve for Q of water. Okay, that's where we want to start. We want to figure out how much the water changes. That's what we have the most information about here is the water. We've got its volume at 100 milliliters, and because water has a density of 1 gram per milliliter, that means that 100 milliliters is also 100 grams. We have the starting temperature and we have the final temperature, and so and then we also have the specific heat of water. Sorry for leaving the units off of that. We want to know Q. So Q equals Cm delta T, specific heat times mass times the change in temperature. So Q equals, so C is 4.184, mass is 100, and then the change in temperature is negative 15 degrees. Right, that's the final temperature minus the starting temperature. So we've got a negative number in there, and what that's going to result in then is a negative answer. Since we're multiplying everything together, we're going to end up with negative 6,276 kilojoules. Okay, so go back to that question in yellow. Where did the energy go? Right, here we're seeing that for water, the energy change is negative. So that means it's losing it. The temperature is decreasing. It's also losing energy in this system. So what does that mean, right? Where does it go? Meaning water lost that much energy. It left, right? To put it another way, if it lost it, it left. The energy is no longer with the water. Where did it go? Well, it went somewhere. It went somewhere else, okay? But, like I want to highlight this, right? That it lost that. It's gone. Okay, so where? Where is an important question. In this system, there's something else in the system, right? So the energy lost by the water is gained by the chemical, whatever the chemical is in that reaction. That's gained there. Energy stuff makes my brain hurt. It feels weird sometimes because we have these positives and negatives. Does it feel hot? Does it feel cold? But it's reasonable to say that as the temperature goes down, the energy decreases. It's leaving. But it's got to go somewhere, right? Thermodynamics says that it has to go somewhere. It has to be transferred. It can't just disappear. Okay? So that's important, right? If it's lost by the water, it's gained somewhere else. So the chemical in the reaction, the ammonium nitrate, its Q, it's going to be the opposite. It's going to gain exactly as much energy as the water lost. And so its figure for Q is positive 6,276 kilojoules. This is a cold reaction, all right? It feels cold. Well, that must make it an endothermic process. What should Q look like if it's endothermic? What does endothermic mean? It means it's absorbing energy. So Q should be positive in an endothermic process. Q should be positive because it's gaining energy. Gaining energy, folks, does not mean feels hot. It doesn't mean that. If you're still hanging on to that, you got to forget that. You got to leave that behind. All right. So the question was about joules per mole, kilojoules per mole. So how do we do that? Well, up at the top, I gave you some additional information, right? We had the mass of the ammonium nitrate, and then I also gave you the molar mass of it. That was easy to figure out. Nitrogen has a molar mass of 14. There's two of those. 14 times 2 is 28. There are 4 hydrogens. Each of those has a molar mass of 1. So 28 plus 4, that's 32. And then we have 3 oxygens. So 3 times 16. Uh-oh, I just challenged myself there. I got a calculator close by. Is 48. So 48 plus 32, that's going to be 80. 80 grams per mole is what molar mass is. So we're going to use that to figure out how many moles we've got. So I'm going to rewrite this here, right? This is our Q for the ammonium nitrate. That's how much energy is absorbed in the chemical reaction process. And then we're going to say if we've got 50 grams of ammonium nitrate, how many moles is that? Good old mole conversion chart here. Okay, so that's going to be 0.625 moles of ammonium nitrate. So just put that into a ratio, kilojoules per mole. Let your let your calculator do the work, and I guess I'm going to rewrite the answer here. It was, I think it was 10,041.6. If I remember correctly, I accidentally erased it. You can check my math on that one there. Okay, so there you go. That's how you have it, right? That's kilojoules per mole. All right. Okay.